cosa faccio io?
Però non c'è il volume.
Non c'è il volume, prova?
Aspetta,
Prova.
aspetta che non sia
Ah no, c'è il volume, sì.
Si sente?
Però di solito si sente recording.
Questo no.
Prova.
Si sente?
Sentite? Un dito in alto, thumb up, se sentite. Thumb up.
Nessuno sente?
Sì, vi sentiamo.
Sì, sentono, perfetto,
Ok,
perfetto. Thumb up, benissimo.
Ok, e torniamo qua.
Okay, so welcome everybody. It's a pleasure for me to, more than a pleasure, to introduce Mariangela Bernardi from Penn, from University of Pennsylvania. I think I met Mariangela and Rav in person in 2005 when I was a PhD student. So I spent 6-7 months in Philadelphia, and was an amazing institute and amazing city. So Mariangela is an expert on galaxy kinematic evolution, dependent on the property of the galaxy on the environment, coevolution of supermassive black hole within galaxies, and she was a student in Padova and moved to Munich for her PhD at the LMU, Observatory of Munich, and then to Chicago for a couple of years. Then she moved to Carnegie Mellon University in Pittsburgh, and a few months at University of Pittsburgh, and then to University of Pennsylvania. And she has an appointment, a full professor at the University of Pennsylvania. She will be around for the next 2-3 weeks in the city, but also in the institute. We hope also to have around here.
I'm enjoying Bologna.
It's more than a pleasure if you could visit us as much as you want. And she will talk today about stellar mass luminosity gradient in MaNGA. And the stage is yours, Mariangela.
Okay, thanks for the introduction. It's a pleasure to be here in Bologna. It's a beautiful city, nicer than Philadelphia. I can assure you that. Okay, so today I will talk a little bit about the size of galaxies, because when we talk about size of galaxy, what does it mean? Is the size that we measure from light, or is the size that we measure by measuring the distribution of the mass of the stellar mass? For many years now, it's more than 2 decades, people observe the size. So you see here, what is called the half-light radius is the radius that include half of the total luminosity versus the stellar mass. And people notice that when we observe galaxy at a higher redshift, at the same mass, galaxies tend to be more compact. Okay, they were smaller. So from the other people, people observe a higher redshift until now with the James Webb Space Telescope. They observe at redshift 8 or even higher, and this galaxy seems to be more and more compact. So there was this try to understand this evolution of the half-light radius. And if you look at the profile, how the stellar mass is distributed, also it tends to be, at least the center part, very similar to what we see at redshift 0, okay? So the central stellar density are remarkably similar to what we observe in Sloan or other survey at redshift 0. And so people talk about this inside-out growth. So galaxies, they grow early on at the central part, and then with time, they were like minor mergers or other things that puff up the galaxy. So, but all this is about the half-light radius. But there is a difference if we consider that, the stellar mass can be distributed a little bit different than light, because there is what is called the stellar mass to light ratio. What do I mean with this? When you compute the half-light radius, as you can see on the left, so as I said, it's the radius, what I call it here RE, that include half of the total light. So it's just the integral of the surface brightness, okay, up till where you measure half of the total light. It's not clear that that is the same as the half mass radius. Here on the right, you see that to compute the half mass radius, so the radius that include half of the total mass, you need to account also for what is called the mass to light ratio, okay? So the mass to light ratio is just the ratio of the stellar mass compared to the luminosity of the star, because we know that depending on the type of star that you have, they have a different value. So low mass star tend to have high mass to light ratio. Instead, the big massive young blue luminous star, they have to have a lower stellar mass to light ratio, because this star, they produce a lot of, they use all the fuel in the core very quickly, and so they produce a lot of light compared to their mass. So why people tend to ignore this mass to light ratio? Just is a little bit of convenience, okay? People assume that it's kind of constant value. So if we assume that the mass to light ratio is constant, when you project, you measure the super brightness, and you plot versus the radius from the center of the galaxy towards larger radii, you see that basically increasing the mass to light is just a constant shift, because it's a log scale, okay? You multiply by that, so in log it's just a constant. However, if you have a gradient in M over L, you can see that where you measure the half of the half mass radius is different than the half light radius, because if you have a negative gradient in M over L, you tend to have the mass more concentrated towards the center. If you have opposite a positive gradient in the M over L, instead you get the opposite effect. So this means that the half light radius is not the same as the half mass radius. Okay, so it's important to try to measure the gradient in M over L. However, for early type galaxies, here, the rest of the talk is related to properties of elliptical galaxy or S0, early type galaxies. Just look at the bottom part here. If you do not have, if you look just the profile in stellar mass computed from using stellar population models, where the initial mass function is assumed to be fixed, you do not have really a gradient in M over L. You see that it's quite flat. Okay, the different color here is just different type of galaxies. I divided the sample in different velocity dispersion, so more massive galaxies are here, the red, the yellow, less massive galaxies are basically the blue, the green, okay? The important thing of this is that you notice that here is basically flat, and here instead you have a gradient in M over L. Why is that? Because there is what is called the initial mass function, the IMF. So the initial mass function is just basically the distribution of stellar masses, okay, when you have a Bartók star. So basically, if you look at just the blue line there, it's called the salpeter, okay, tell you that you generate a lot of low mass stars, and then you generate less massive stars, okay? Massive stars, as I said, they are short-lived. Okay. Massive stars, short-lived, are the blue, very massive, they go up to 60, 80 times the mass of the sun. Short-lived, they are very luminous, they reach like, a million times of luminosity of the sun. And they have low M over L because given their mass, the luminosity is so high. The scale in luminosity for stars is the larger scale that you can have. You go from 10 to the minus 4 to 10 to the 6 times the luminosity of the sun. So it's a huge scale. The mass instead that you go, from the famous 0.08 solar masses to about 100 solar masses. So the scale in luminosity is much larger. So they have low M over L and they are hot. Temperature that reach 30 or 50,000 Kelvin. Vice versa, low mass stars, instead they live for a very long time, for way longer than the life of the universe. Okay, in the main sequence at least. They have low luminosity, high M over L, and they are cooler. Okay, temperature of down to like 3,000 Kelvin or so, or even lower. So now you understand that if the IMF has a different shape, instead of going up steep here, it is a little bit shallower, okay, you produce less low mass star. So this means that the distribution of the M over L, the overall distribution, is different depending on which IMF that you use. So that is, if you start accounting for gradient in the IMF, so that, for example, massive galaxy, they have an IMF that is more like the blue line compared to the low mass galaxies that are here, you can have also a different distribution of the mass to light ratio. But vice versa, it's not only from galaxy to galaxy, also inside an individual galaxy, okay? If in the central part of the galaxy you are dominated by an IMF that is different than the outer part, you generate a gradient inside the galaxy that is what you see here. Instead, if the IMF is kept fixed, you basically do not have a gradient in the M over R. Okay, so now I'm an observer, so about the modeling of the IMF, I'm not really the expert, but it's kind of not so simple to model the IMF because it depends on many things. Why do we have to have a different IMF? So can be metallicity. If you have a higher metallicity, you tend to cool easier, and so you form a small fragment, so you can increase the number of low masses. Another property that can change your IMF is the star formation rate, because if you generate a lot of, for example, of massive star, you can have a lot of stellar radiation pressure, and so you heat up, your surrounding, and so you can form larger fragments. And so basically, you can have what is called more a top-heavy IMF, like look at this red line, you form a larger number of high mass star compared to low mass star, or bottom heavy, where instead you see the drop in the high mass star, you form a more low mass star. But all this is complex because, for example, when the density is very high, when you increase the metallicity, I said here that the metallicity, with the higher metallicity, you have more cooling, and so you form more smaller fragments. However, if the density is very high, when you increase the metallicity, you become more, the gas become more optically thick, and so that traps the radiation. And so the metallicity has the opposite effect in that case. So another thing that is important to account is that, especially when we go to higher redshift, the CMB, the cosmic microwave background radiation, is warmer, okay, because of the expansion of the universe, and so also that has an effect. So this is just to say that it's not easy to model the IMF. Okay, assume now that they know how to model, and we use the stellar population models, and they are correct. That is an assumption. Okay, so that is a big one, but we assume that. So people start try to measure if there is actually variation from one galaxy to another. So you take some spectral features. So you have the spectrum of a galaxy. Here you have the black line. Here is what you observe. And the red and the blue lines here are the models. And so the red is fixing the IMF to the Milky Way, so like what is called Chabrier IMF. That is something that is not as steep as saltpeter curve, like a lower masses. Or to let something else more like bottom heavy, some other IMF here. And you can see that the variable IMF fit kind of this feature in a better way. So you have many of these features, okay? And so you try to have the best fit to your spectrum. And so what people observe is that as you go to more massive galaxy or galaxy with the larger velocity dispersion, okay, they tend to be fit by a different type of IMF, more like saltpeter. So what I mean is massive galaxies tend to have an IMF that's more like this blue line, and lower mass galaxies, they tend to have more like this pink or red line, okay? That is the difference, basically. You produce a larger number of low mass stars for more massive galaxies. Okay, so why is this important? Because people notice that if you compute the dynamical mass. The dynamical mass of a galaxy is computed with the mass is r sigma squared, okay, with some factor in front. Assume that factor is constant at the moment, okay? So people notice that if you compare that dynamical mass to the stellar mass, instead the stellar mass is computed, you observe the light, and then you fit the color or the spectrum, and from the model, you get the mass to light ratio. So you multiply the L by the mass to light ratio, you get the stellar mass. So that is the stellar mass that you compute, fitting the spectral energy distribution of a galaxy. That is different than the dynamical mass. So what people notice is that going towards larger velocity dispersion or more massive galaxy, let's say, there was a discrepancy, okay? The dynamical mass tend to be larger than the stellar mass. That is why they start accounting for this variation in the IMF, because they said, okay, this massive galaxy, they need an IMF, okay, that is different than the lower mass galaxies. So if you account for this variation, you basically you can take into account about this discrepancy. You are able to solve this discrepancy. And but all these, okay, you vary the IMF from galaxy to galaxy, but inside one individual galaxy, the IMF is fixed, is constant, okay? And so there have been many papers about this. But then at a certain point, people start realizing, oh, let's check if actually there is also variation inside a galaxy. Okay, not only from galaxy to galaxy, but inside the galaxy, does the central part of the galaxy have a different IMF compared to the outer part? And that is what they start observing. So you can see here a gradient. So the central part of the galaxy tend to have an IMF that is more bottom heavy, so more fit by like saltpeter compared to the outer part. All this has been done always with a sample of 10 objects or even fewer. And not everybody agrees. Some people say that there is a gradient, other people say that there is no gradient. Okay, this is flat, this is flat. So there was a little bit of debate. Oh, no, sorry. I don't know where I am. Okay. So what is possible to do now instead is not to use just 10 galaxies, but to use a larger sample. Thanks to the introduction of this integral field spectroscopy, it's possible to observe multiple parts of the galaxy at the same time. So you have many fibers or small slits, and you can observe from the center of the galaxy to the outer part, both photometry, you have the image, so you have the photometric measurement, plus you have all the spectroscopy. So the largest survey is MaNGA, is the largest one that include about 10,000 galaxies. And then there is SEMI, that is about 3,000 galaxies. And then there are a little bit smaller sample. We talk about Atlas a little bit like more than 10 years ago, and then Khalifa Massive, and there are others. But MaNGA is a very nice survey. So it's part of the Sloan Digital Sky Survey. And what is possible to do, since you have so many galaxies, for which you have, about 100 spectra for each galaxy, is to try to make a composite spectra. Because although you have a very high signal to noise in the central part of the galaxy, signal to noise for the spectrum larger than 100, as you move towards the outer radii, the signal obviously drop, become fainter. And so it's not enough to be able to measure these particular features with very high precision. Because just to give you an idea, I don't know if you're able to see here, but the different color from the red, yellow to the green, that is the kind of differences that you want to measure here. And so you need a very, very high signal to noise. So what we did was to divide the galaxy in different luminosity beam and different velocity dispersion, so such that then we have the galaxy very similar in properties. We divide them, elliptical, slow rotator, fast rotator, zero. So anyway, we took galaxies that they were very similar in properties, and we combined them. We combine all the spectrum, okay? And so in this way, you reach spectra with signal to noise of 700, 800, very, very high signal to noise. And so we were able to measure all these different features. And doing this, we were able to, using the stellar population model, measure well the IMF gradient. So here you can see, so up here are different beams in stellar mass, or no, actually this luminosity, okay, sorry, magnitude. So these are faint, and these are bright galaxies, okay? And then we have a different beam in velocity dispersion. So these are galaxies with a higher velocity dispersion, up to 320 kilometers per second and down to 100. And then we divide also in elliptical, slow rotators, elliptical fast rotators. There are some elliptical galaxies that show some rotation, and the lenticular galaxies. So anyway, the bottom line here is to observe that if we analyze the spectral features with models, we have that the central part of galaxy tend to have an IMF that is more similar to the salpeter, while the outer part is more similar to the Chabrier. Okay, there is a gradient in the IMF. So if we account for this, so then also the mass to light ratio give a gradient. Because you see, if I fix the IMF to Kruppau to Chabrier, there is no gradient in M over L. Okay, for this type of galaxy, for these early type galaxies, if you fix the IMF, there is no gradient. Because you could have a gradient. For example, if I take a galaxy that I have a bulge with the old stellar population, and I have a disk with the young stellar population, I can have an M over L gradient similar to this, just because this is old star, these are young star. Old star, as I said, they have high M over L. Young star, they have low M over L. So I form a gradient just because of the different stellar population.
Sorry, to derive the mass to light ratio, you use only photometry or also spectra?
No, this is spectra. This is all from,
spectra.
Yeah, this is all from spectral features.
The mass to light ratio from the spectra.
Yeah. So we fit, so this is, so I have another slide, or maybe we can talk later. Because from spectroscopy is, so if you have if you take color, okay, photometry, what you are doing is basically broadband, a big piece of the spectrum, okay? And the problem there is that there is a big degeneracy between age, metallicity, IMF, dust, okay? So it's very difficult to know if a galaxy is red because it's the age, or if it's higher, more bottom area IMF, or what is. So with the spectral features, it's the only way that you can break. It's very different from color. From photometry, it's very difficult. That is why this kind of work I will show you now is possible to do basically. Yeah. So, okay. So you measure the IMF, but you measure also other properties like age, metallicity, alpha enhancement. I just skipped this. Okay, going back to the side. So the difference between the half mass and the half light ratio. So as I said, it depends on the gradient in M over L, okay? But it depends also on the shape of your light profile, because this is, you measure the light, you measure the shape of the surface brightness, and this is what is called a Sersic profile. So if the Sersic index, this n, is larger, you get more like this magenta line. If it's like a disk, okay, an exponential profile, you get like the blue line. Okay, that is an exponential profile. So you can see that when you go to larger Sersic index, you have more like light at the center. There is like a more peak at the center and the tail outside. So now you can imagine that if you have a gradient in M over L with something that is more peak at the center, okay, the effect is larger. So you put just more mass at the center part than if you have more like an exponential profile. And that indeed is what you observe, okay? So in this case, I just did a toy model in which you use this kind of steeper gradient in M over L, and then I increase the Sersic index. And here in the y-axis, you see the ratio between RE of the mass and light. And you can see that the area of the mass becomes smaller compared to the light as I increase my Sersic index and as I increase the gradient in the M over L, okay? So this is just to, to introduce a concept that you can change the distribution of the mass compared to the light because of different properties, the property of the light, but also the property of the M over L. And this is basically the result, okay? So if we observe the famous size-stellar mass relation, it's important to define what is the size. So if the size is the half light radius, you get the dotted line here. If the size is the half mass radius, you get the solid line. And as you can see, there is almost a factor of 2 here. It's a more than 70% effect. It's not a small effect. Okay, this galaxy are much more compact if you consider the mass, the distribution of the mass, just because there is a gradient in the M over L. And so at a high redshift, it's much more difficult. You cannot look at the features. So at a high redshift, what they do is actually was using the color, okay? And so, but at the high redshift, for example, they assume that the variation in the color is just age. They fix the metallicity, which is wrong. We know that there is variation metallicity as well, but it's what they can do. And so you can see here, for example, redshift 1.2 or redshift 2.2. So the solid line is the half mass radius. The dotted line is the half light radius. So you can see that if we look just the mass, so now between redshift 1.2 or even redshift 2 to redshift 0 is not, there is not much difference. There is some difference, okay? But it's not, as people claim, going from here to up here, okay? So that is something that we have to take into account. Maybe the evolution in the half mass radius is smaller than what people claim. And this is important because most of the simulation, they just assume that it's the evolution size as if the half light radius is the same as the half mass radius. So another important part of this gradient in the M over L inside the galaxy, remember at the beginning I showed you this, that people start talking about a variable IMF galaxy to galaxy because there was this discrepancy between the dynamical mass and the stellar mass, okay? At larger velocity dispersion or more massive galaxy, there was the dynamical mass was larger. So people said, oh, we resolved this just saying that the IMF changed from galaxy to galaxy, okay? More massive galaxy, they had different IMF. But however, notice this. Okay, so how do you estimate the dynamical mass? The dynamical mass, first of all, you have the projected stellar mass profile, that is just your surface brightness times the M over L, okay? So then you have the three-dimensional stellar mass profile, it's just the integral of that, and it gives, the density. You compute the dynamical mass integrating the density, okay? Now, however, inside this, because you had this M over L, and this nobody knows what it is, okay, you had basically a 0 point that you can move up and down. Okay, so how do you calibrate that 0 point? You calibrate using the Jeans equation. And so you can see that, Jeans equation is complex. Here is just an approximation, assuming no velocity and isotropy. But the bottom line, you have that there is the M over L here, there is the M over L inside here, M over L inside here, and you have the velocity dispersion, okay? We observe the velocity dispersion. So M over L, assume that here cancel out, basically you are left with an M over L. So using the velocity dispersion, you can set what is the M over L of your galaxy, okay? That is what people did. But it can be a constant, or it can have a profile. So if it has a profile, you have to integrate properly, okay? It's not just a constant that you take out of the integral. And so this is what basically the result. So this is the same thing as I was showing before. So it's the ratio between the dynamical mass and the stellar mass from stellar population model. You can see if you assume just a constant here, okay, you can see that there is the discrepancy. So the dynamical mass is larger than the stellar mass, okay, from stellar population. If we start assuming, that, okay, we're trying to improve the measurement of the dynamical mass, assuming that there is a shape in the light profile that is different sources, you can improve a little bit, the scatter become a little bit smaller, you get a little bit less of a slope here. But when we are going to account also for a gradient in the M over L, you can see that basically the discrepancy almost disappears, okay? So basically, as you can see, this is the stellar mass function. You can see this is the black is the dynamical stellar mass mass function, and this is instead the stellar population, the blue. So if you account for the M over L gradient from the solid one, this is just the difference, okay, between what you measure without and with IMF gradient or M over L gradient. The black, the solid black becomes the dash, and the blue become the dash blue. So you can see that the effect of an M over L gradient is larger for the dynamical mass than for the stellar mass from stellar population, which typically people ignore this. The dynamical mass is completely independent from stellar population, okay, from stellar population model. Instead, it's not true if you do a proper job to account also for gradient in the mass to light ratio. And so that is what you get here. So basically the discrepancy here disappear not because you change the IMF from galaxy to galaxy, but it's because you assume a gradient, okay, in the M over L inside the galaxy, which is a different concept, okay? And so this is the conclusion. Basically, accounting for M over L gradient inside the galaxy, radish is 0, here is all radish is 0, okay? And this, remember, these M over L are IMF driven. It's not age, it's not difference in the population, it's just a variation in the IMF, okay? So we have that the dynamical mass decreased by a factor of close to 60%, and is larger than the effect in the stellar population mass. Okay, stellar population is an increase of 30%. The size, if I compute the radius that include half of the stellar mass, okay, this is smaller compared half of the total light, okay, by a factor of 70%, okay? And also remember that it depends on the shape of the light profile. As we go to larger Chersik index, the effect on the stellar mass is on the size that include half of the stellar mass is larger. So basically we have consistency between stellar population, stellar mass, and the dynamical stellar mass, just assuming gradient without, variation. There could be also variation from galaxy to galaxy, but just with the gradient, you basically solve the problem in the difference between dynamical stellar mass, and also there is less evolution in the size stellar mass relation. And so I think this is important for models because if you start accounting for IMF gradients, you have less merging. You need less merging to basically solve this increase in the size of galaxy from a high redshift to lower redshift. And I stop here.
Thanks. Questions?
It was very interesting. Can you please explain again how you determine the AMF variation inside a single galaxy? What steps did you do, and what parameters are related to?
Yeah, I didn't show the slide because it's a little bit technical. Let me see, because I'm blind. Okay, so I think this could work. Okay. So basically, what you use is what are called the leak indices. Okay, so you see here, these are features. So you have the spectrum, you have absorption lines. So this is H data, is a Balmer line, transition second level to third level. So this is more indication of age more than the metallicity. This is magnesium, combination magnesium iron is more like metallicity here. So the dots here that you see here, these are data from the stack spectrum, okay? And so I divide in slow rotator and fast rotator. So the circular slow rotator and fast rotator are the square. And the different color are two velocity dispersion beam, okay? Yellow are more massive galaxies, the green are less massive galaxies. But the important thing is that if you look here, these thin lines, these are models. In this case, it's the Miller's model. And so the metallicity, basically, you go from, the metallicity increase in this direction. So the thicker line, blue line here is solar metallicity. And this is less than solar, this is higher than solar. Okay, so metallicity increases from left to right. Age is from top to bottom. So this is 4 billion years, this is 8 billion years, 10 and 12 billion years. Okay, so here you can break the age metallicity. And so this is the center of the galaxy, and this is in out. You go towards the outer part. This is for age metallicity. This is for what is called the alpha enhancement, okay? The amount of basically magnesium alpha particle compared to iron. And this is important for the IMF. So for the IMF, we use more features like titanium monoxide, features that are more, if you look at the spectrum, okay, I can show you this maybe. If you look at spectrum of a star, so this is a level of Astro 1, but give you an idea. Okay, so this is the typical star. If you look at star O, B, A, F, G, K, M star, okay, these are hot star, long-lived, short-lived, very luminous, as I said, 1 million times more luminous than sun, and these are the cool star. So you can see in the spectrum of a cool star, you see that there are a lot of bands. Okay. So, but the difference in the spectral feature that you observe between this spectrum and this is not different metallicity. Okay, it's just the temperature that set the difference in the spectrum. Okay, and so so if we wanted to try to see, do I have more this type of star compared to this type of star? Okay, what do we have to observe are features that are typical of M, okay, star. So there is the titanium oxide. Okay, so that is what we are trying to measure. So we expect that if we have a larger amount of low mass star, you should have a larger amount of this type of elements. Okay, but the problem is that the amount that you have of titanium depends also on the metallicity. If I have higher metallicity, I will have also higher. That is why you have to break. If I go back to the other slide, if I can find. Where was I? Let's see here. This one.
These are all a simple population.
Yeah. So this is the same. This is only for elliptical galaxy, basically. Already with S0, you are at the limit. So this is assume a simple single stellar population. And so this is, again, you see here you break basically is a different metallicity, different alpha. So if you look at the purple, magenta lines here, this is a different alpha enhancement than the blue line here. Okay, so the alpha, alpha enhancement, IMF, sorry. So different IMF, you go from the cyan grid here to the pink one. Okay, you increase that. And then you have to use all this line such that if I look at point here, this point has to have the same age metallicity than I get from this other grid here. So you have to make such that you get really the same age metallicity from any of this grid. So you have to do that, you have to increase the IMF. Otherwise, it's impossible. Just to give you an example, take this point here. Okay, you see it's in this dot dash line. Here in this plot, it would be here. Okay, so if you take this yellow, star in this plot, to have the same age metallicity should be down here. Instead, you see that you observe up here. Okay, so that is why you know that it cannot fit. You have to change the IMF. Okay, so that is what we are doing. And going back to what you were saying before, here you can see this is called G-R color, and this is the radius. Okay, so this is the color profile from the imaging. I have it because I have also the the photometry. So from the imaging, I get this color profile. If I do the spectral energy distribution and I use the filter, the same filter that is Sloan, that we use in Sloan, okay, I get something that is different. It's basically the solid line here, okay? And so this means that there is some problem in how the spectra are really normalized, calibrated, okay? If I compute instead the models and I do the proper work using the leaking indices, I get more in agreement with the photometry. So this is basically the dashed line or dotted line here, okay, are, if I use the leaking indices, I compute the color from the model, and those agree better with what I see from the imaging. Okay. Instead, if I use the full spectrum, because sometimes you said, okay, I have the spectrum, why should I use just only 10 lines and waste all the rest of the spectrum? Is a pity. So why we do not use the full information? And the problem is that to calibrate the spectrum is not an easy job, okay? Because you have the proper calibration, you have problem of dust inside galaxies. And so when you use small features, they are much less sensitive to the reddening, to calibration effect. That is why.
Any more questions from the remote audience? We are a bit late than usual, I guess.
Yeah, sure.
Yes.
I wonder, do people do simulations, because there are galaxy formation simulations, do any of them do with spatially variable IMF?
Yeah, so now they start accounting for the IMF variation, and they try to incorporate that. You can, you put by hand and you have to assume a gradient in IMF, and it's possible. Yeah. But the problem now is still, why the question is that you can put an IMF gradient, it's not a big deal, but the problem is why.
Right, they could have tied to metallicity or to stuff.
Yeah, right. That is the problem, is that you have to explain why do I assume this. So there must be the metallicity, there must be the star formation rate, and if you go to high redshift, the CMBS is important. So you have to account by all these factors.
Okay, then we can thank the speaker again.
Okay.